you hear me? Well, we have been talking about process synchronization, and we talk about the producer-consumer. And this producer-consumer shows you that when you get into the concurrency domain, the way you have to write program is a bit different. So we're going to start talking about the producer today. So I have a producer here. We say produce an item. We have a buffer. We use the same number of. So the first thing we need to do, resume, is to use a semaphore called pt1, which means that that full semaphore, initially the buffer size, we're going to declare buffer size, which is 4. So it will control when the buffer is full, which means if you, the producer-consumer, are processes that are running constantly, iterating. So we need to stop the producer or stop the consumer under certain conditions. If the buffer is empty, we have to stop the consumer because we cannot consume from an empty buffer. If the buffer is full, we cannot produce more items because we don't have a place where to place the item. So this is to control if the buffer is full, and then we stop the producer. How? If initially 4, if we go 4 times, before means -1, right? Then -1, then -1, and then -1. Eventually, we get a number less than 0, and then we stop. Right there, the program will stop, but the buffer is full. Then we need another semaphore, which is empty. I'm sorry, mutex, for mutual exclusion, which means we only need one process inside the critical section. Otherwise, we get into a race condition. Then assign value to the buffer. Let's say, we could say, for instance, we place the item produced here into buffer I, with I initially 0. Okay? So we place the first item here. Immediately, we have to do an increment on I. So the pointer, the index, moves to the next location. And then we have to ask if I equal 4, because it's 0 plus 1 plus 1. I mean, where here we say place the item, increment by 1. 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 So this is 4. Then I equals 0. Why? Because 1 is full. The producer has to wait until the consumer starts consuming item, taking item from here. And the consumer is going to, if this is, let's say, I, then we're going to have another variable, let me call it K, associated to the consumer. So the consumer is always behind the producer. And then we say here B mutex. That means that we are out of the critical section, we unlock the critical section, and some other process is able to handle the buffer. After that, what do? We have to do a P operation, a B operation on the empty semaphore. Why? Because we have a semaphore which is empty, initially 0. When the empty is 0, then the consumer cannot consume. It's a way to stop the consumer, but B of empty means that we increment the value of the semaphore associated to the consumer, and we're telling the consumer that there is an item there. Okay, remember the B increment, P decrements. And then we could say that this is a process that is just iterating. In an operating system, there are many processes that are just constantly running. Okay? And then on the other side, we have the consumer. The consumer is going to apply a P operation on empty. If empty is initially 0, then, and we don't know which one of those two processes the OS is going to dispatch. Because the operating system applies a scheduling algorithm, the one with the highest priority, according to what the priority is, will get the CPU. If the consumer gets the CPU first and the buffer is empty, we have to stop. In this case, we know that the producer produced an item, and here we're incrementing the semaphore empty by 1. So that goes to 1. So if the consumer gets the CPU, then applies P on empty, and the value of the semaphore is telling the consumer that there are items in the buffer. All right? After that, we need to enter the critical section. So as we need only one process in the critical section, mutex is equal to 1. That means that we accept only one process within the critical section. Full is telling me we only admit 4, let's say, items in the buffer. So practically we're counting. Then we have something similar to this. We do K gets K plus 1, okay? And we can have, for instance, K equals 0, and then we start 1, 2, 3, 4, or we can have K equal minus 1, increment by 0 this here. And then we do, in this case, what we do is, let's say, value gets BK. So we're taking this item from the buffer and assigning it to the variable value. After that, the same thing. We have to check if K is equal 1, then 4. Then K equals 0. Same thing, if we consume this item, and then this item, and then this item, and then this item, we have to go back. We have a B mutex, and then we have B4. This is to increment the semaphore 4, because that is the consumer telling the producer that there is a new free space in the buffer. And then we consume. Whatever consume value is, printing the value, sending the value somewhere to a network, whatever it is. Okay? So this is the producer, consumer, or bounded buffer, producer, consumer. And we're using a new kind of programming that is concurrent. They call it concurrent programming, but what is concurrent is the execution. Concurrent execution of sequential programs. Okay, so if we write a program with two functions, producer and another consumer, and we have constructs to initiate them to run concurrently, we have these two running concurrently, and if we're talking about apparent concurrency, they are doing process of sharing the CPU. If we have two cores, two processors, then we can have them running simultaneously. Okay. This is the critical section, and this is the critical section. All right? Any questions? Is that clear? Okay. I would like you to give me a solution to a producer-consumer problem with one producer and two consumers. Can you do that for me, please? I have a case here for this case here is producer, consumer. I would like to have a solution for this one. In the producer, practically you don't have to do anything. Well, let me change the problem. Let me give you an easier one. Allow me to do this, please. Okay. We have one producer and two consumers. The producer has to produce, similar to the first one, produce item from buffer 1, and after that produce an item for the buffer 2. We're going to do that one after the other. And the consumers are practically the same thing. They just consume. Practically that is the consumer. The things that we have to use are variable and index, which is different K1, K2, K2, etc. But let's see how would you do with the producer. Yeah.
So the producer fills alternating.
Supplement. Produce an item for buffer 1 and then an item for buffer 2. We have that. Check. First question, how many semaphores do we need? For instance, for 4, only 1 or 2? 2, because each fold is associated to a different buffer, and they are different sizes. How many semaphore mutex do we need? We're going to use 1. The problem with 1 is that every time that the producer is going to place something in a buffer, blocks both buffers. So with 2 is better because you block the first buffer, place the item, continue, move to the next. If you block the second buffer too, in insert something there, the consumer 1 is able to consume from the buffer. So 2 is recommended. 1 works, but then every time you try to put an item in a buffer, you block the other one. Okay? And for empty, similar to 4, we need 2. So we need 2 of each one. This could be approximately the final. Write a producer similar to the one we have there, and then after that one you write another. The second part of the producer is to replicate that using other full, other mutex, and other empty, another index. And then for the consumer, you have 2 independent consumers, similar to the one we have there. So you have one with K. The semaphore have to match for one of them the upper part of the producer, and for the other one the bottom part of the producer. So are then trying the 2-1 setup. This is the first one, right? This is for what issue to be full. And this, they are different sizes, right? But if the first one is 3 and it's full, then this one is 12.
excuse me. So you produce an item, then before vmod takes insert, you have to do it step by step, insert vmod, and then yeah, but this you need two full semaphores, because if you use the same semaphore, when you apply P4 here, you block that the consumer consumes for the second one. So you need two different, let's say, if the P apply P4 in the second one, at full control the first one, you're blocking the both of them simultaneously.
P4.
Imagine that P4, if you say P4, you're using P4 in both of them, right? The first problem is that one is size 3 and the other is size 4. So you need two P4 semaphores. One for the first buffer and one for the second buffer. So you have to do P4 1, P-mutex 1, PMT 1, and then P4 2.
Okay.
Okay?
Thank you.
Okay, let's find something big. Just target, I don't know what it means exactly, but let's say target consumer 1. So how do you choose the target? Yeah, what you have to do is like this one, you create an item, do mutex for buffer 1, say mutex 1, insert the item. The same thing we have there. If you finish that one, go to the second one. But what you're doing there, that can be done, but that implies something different. How to choose the buffer. That's another problem. So you have to repeat that algorithm twice, but before one, you mutex 1 and you empty 1 to work with the buffer 1 because it's size 3, the other is size 4. And when you finish this, continue